Good morning. Thank you all for being here, and thanks for inviting me to speak. How do I? I'm sorry. I'm going to just go to the desktop and find this myself. So I'm the director of publishing for the American Astronomical Society. It's the largest professional organization for astronomical researchers in the world. We have somewhat over 6,500 members, which is half or more or less, roughly, of the number of professional astronomical researchers in the world. That number is between 12 and 20,000, depending on how you count. We publish scientific research in two major journals, the Astronomical Journal and the Astrophysical Journal. Those are both older, actually, than the American Astronomical Society by several years. We didn't start these journals. We inherited them. They're significant journals. The impact factors of 5 and 6.5 are big in astrophysics. And these are large journals. As a family, we're publishing more than 4,000 articles a year. The operation that we have is comparable in size to that of the Royal Astronomical Society, which you heard Chris Linto talk about this morning, and also about the same, comparable in size to the European Journal, which is Astronomy and Astrophysics. Our program is actually somewhat larger than either of those two, but those are the sort of the major astrophysics publishing operations. The Society has been publishing data in its journals as has everybody who's been publishing scientific journals in one form or another, charts and graphs. I imagine Todd will talk about that and give some examples of that in his talk. But we sort of got explicit about it in the mid-1950s when a supplement series was added to the Astrophysical Journal explicitly to publish what were the data-rich papers of that time, which was basically extensive tabular material. As we've moved to digital publishing in the last couple of decades, that stuff's moved out of print and into online, and so we've been accepting digital data in the journals for about 20 years now, in a number of data formats and with a number of delivery methods. For a while in the 90s, we produced coasters. Did about 9 of these over a period of 4 years, from 93 to mid-97. So there's actual machine-readable tabular data on these CD-ROMs. It was distributed to the subscribers. It went out in the community that way. By mid-97, it was pretty obvious that the kind of content we were getting in these was going to easily be deliverable on the networks. So we discontinued the CD-ROMs and just delivered that content with the journals online. Those journals went online sort of in a staggered way staggered in time way, in the mid-90s from 95 to 97. So we've also had these journals online for a long time. This is a diagram sort of that shows the problem that we're confronting in the abstract. This graphic is from a guy called Brian Heidorn. Brian was at the NSF when he built this chart, or when he made this abstraction. He's now at the University of Arizona, which is where I am. And this is just a power law. When you hear scientists talk about a power law, this is what one looks like. And what he's graphing here is the size of the data sets and then versus the number of them. So when you get very large data sets, there are relatively few of them. As you get smaller and smaller data sets, the preponderance of them increases. And his point in the green versus gray is that the large data sets, which live at typically well-funded large archives, are pretty well tended. They're taken care of reasonably well, and we're worried about that. We're worried about that long tail of essentially what Brian calls orphan data sets. This is, beyond being an abstraction, actually somewhat relevant in the real world. So this is that chart with a few of the data centers in astrophysics on there. The big ones are I didn't put them in any, sorry, they're just on the graph where I could slide the text. It doesn't mean to imply relative sizes. The Space Telescope Archive is the top one, the Multi-Mission Archive. An infrared archive at JPL and Caltech. The Chandra High Energy Archive is at Harvard. And the Sloan Digital Sky Survey, those are all spacecraft missions, well funded by NASA. The data centers are very well funded. The Sloan Data Survey that we were talking about earlier today is a ground-based system, also very large and well funded and well tended. At the very far end, I've put the journals, and CDS is a data center in France that holds stellar tabular data. Along with a variety of other things, but we mostly tend things that are very small. We think we do it very well, so we think that the far end is pretty well tended, but there's this sort of discouraging then gap in the middle of things where when we ask for data to go with our tables and figures. People tend to get creative, right? Scientists are creative, innovative. They like to give us more. They push the envelope. So we get driven in the journals to getting more and more complex and larger objects, which are not particularly well suited for delivery in a journal's environment. So this sort of maps out a continuum. I think as this session was conceived, we're looking at this as a continuum, and this is a way sort of to graphically represent a continuum. And for me, I think that it's the moderate stuff in the middle that's causing us a problem. There's a sort of discouraging gap where we're not, in astronomy, where we're not addressing that, and I think that's fairly common. We sort of look at it from the standpoint of that graph as there's data in the journal, data outside the journal, and we're trying to create an ecosystem for data by nurturing a variety of partnerships. This slide was written for astronomers, so there's lots of acronyms on here that you aren't necessarily needing to know, but down at the bottom are a couple of things that you will recognize, and those are sort of our attempts to interact with the wider community through DataCite, Crossref, and other organizations that facilitate the linkage. What we're doing right now is taking a variety of data sets, mostly machine-readable tables in sort of a structured ASCII. That sort of encompasses what's in the top 3 bullets, and then there's a number of other kinds of things. FITS is a very widely used data format in astrophysics, and that would be for sort of direct images and spectra and things like that. And there are other sorts of things as well that we have to deal with. This is sort of what it would look like online. The data behind the figure, when we're trying to provide data behind the figure, this is a push we've been doing in the last 2 years. Pardon me. This problem, these slides aren't happening in front of me. I just want to say that we've been doing machine-readable tables since about 2001. Sorry, it's okay. It's okay. I can see it. We've been doing machine-readable tables, but warning for the rest of you, yeah, the slides aren't advancing here. It's working great for the audience. So we're participating. We're with you. We've been doing machine-readable tables, which is, right, just turning tables in the journal into machine-readable form since about 2001, with an increase, it's doubled sort of in the last 10 years. That's not a huge number outright, but it's a lot of work to make these things. We've moved into trying to get more data behind the figures when it's in the same thing, and a variety of other things. So they come out looking like this. You get the structured ASCII files you see in the bottom, from which you can reconstruct the plot if that's what you want to do. Reproducibility is a big word in why we want to have digital data available. I think it's not that big a deal, and I'll show you that at the end. And what we've been doing then lately is to try and understand what we have in the journals, taking an inventory of our content. A lot of it is line art. We have some direct images and a little bit of stuff that's just diagrams. There's no data behind it. It's just cartoonish. And then the green wedge is things that are layered, where we have graphics in the journal that are multiples of those things, where we have to separate out the layers. But we know what to do with the line art because the data behind that's fundamentally tabular. And we're trying to get more of that. I want to just talk a little bit here at the end about a project that we've done with some NSF funding. that's allowed us to survey the community about their attitude, the astronomical community about attitudes about data sharing and use. We've done some other things as well. The NSF was interested in the first item, and we engaged some thought leaders in some other things. We were responding to some of those items that were popular a couple of years ago. This was conducted for us by the Statistical Research Center at the American Institute of Physics, and we had a very high response rate, and not terribly surprisingly, at least to me, was that astronomers really don't have a problem sharing data. The survey looked at people's attitudes in sharing data out and also asking others for data to use. There was very high response rates of what they've done in the past 2 years, and even higher response rates in terms of their expectations for the future years in both patterns of using and reusing data. And finally, we did some cross-cuts. We can see how the data was contained. What I would really like to point out is for the people who reused the data, the overwhelming reason that they used it was to explore new questions. The third bar over, which is pretty small, is because they wanted to reproduce or redo the work. And that's really what we're trying to do. I think all of us, but certainly at the American Astronomical Society, in trying to serve the community of scientists, is to allow them to do what they do, which is explore new questions and pursue new investigations. Thank you.
Thank you. Okay.